Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome to this Australian Water School webinar brought to you by IceWarm. This is what gets me up in the morning, speaking to the smartest minds in the water sector about their smartest ideas. And this highly regarded webinar series engages leading thinkers in the water sector globally. Craig, Mitchell and Ben will lead us on a discussion around 3D computation, fluid dynamic and environmental modelling. My name is Trevor Pillar. I'm the National Partnerships Manager here at IceWarm and Chair of the Australian Water School webinars. Great to have you here for today's webinar. Once again, this webinar has attracted a huge number of people across the globe. You can see it there on your screen. Presenters today, Craig, Mitchell and Ben. Craig's a civil engineer. Come on screen, guys, that'd be fantastic. Craig's a civil engineer and project manager with international experience, includes 15 years with the US Army Corps of Engineers. Mitchell is from 2Flow FV. Forgot to mention Craig, Surface Water Solutions. Yes, got that right. Mitchell is with 2Flow FV, finite volume. Mitchell is an environment engineer with 15 years experience. The role is 2Flow FV product lead. He delivers software development at BMT in Brisbane. Ben is with Alden Labs in the USA. Dr. Mader is a civil engineer with particular experience in three-dimensional numeric modelling of hydraulic structures related to water supply. I'm going to read the lot, Ben. Fish passage, it's so interesting. River mechanics and restoration, sediment transport and turbulent mixing in stratified environmental flows. If we haven't got the right team here today, I'll hit my hat. This is great. Craig, lovely to have you from the beautiful WA.
It's bright and early here out in Perth.
Thank you. Mitchell, wonderful to see you from Queensland. Brisbane yet?
Yeah, it's good to be here. Thanks for having me.
Lovely view out your office window. And Ben, you're coming to us from the beautiful USA.
That's right. Sunny Fort Collins, Colorado.
Tell us in one sentence, each of you, why you do this at such odd hours of the day.
Well, if we go in order here, I think this is something that it's just the natural evolution of things. When we get better and better computing power, you have abilities to do things that you couldn't previously do in 3D. We can now put to great use. Including this webinar. Mitchell?
Yeah, I've always been a bit of a weather nerd, so you sort of slowly progress into modelling, and we're all a bit techie, so we get more and more detailed as we go.
Ben?
I grew up fishing and paddling in creeks and rivers and chose a career that would allow me to pursue those interests.
Fantastic. Look, that's really great. We've got a couple of poll questions that you answered. Thank you so much for that. Here's the solutions. Oh, well, here's the responses. Any comments, gentlemen? Take it away.
Yes, as we typically see, it's mostly consultants and mostly no experience. I mean, this is something that's odd. Whoa. Usually when we host a webinar, it's the people attending have actually got experience in the thing that we're talking about. In this case, this is a bit odd. Most of the people have actually never done 3D assessments and are on board to learn how to do it. So hopefully if we ran another one of these a year or two from now, the results would be different. Ben, Mitch, any comments there?
No.
I think it's great that people are getting more interested in it, and hopefully they come away today with a bit more knowledge of the different things you can do.
No, absolutely. I would agree with Mitchell.
We'll make it even better discussion. We're going to hand straight over to Cray now and get this thing cracking. And also, I forgot to mention, thanks also Brian Fox. Yes, thank you, Brian, for joining us. Do come on screen if you wish, but do join us on the Q&A. We'd really appreciate your expertise in this. Is that right, Cray?
Yes. We'll get Brian's input while Ben is talking and while the presenters are going, so that they're not distracted by the Q&A screen. We've got other experts on board who can answer your questions through the Q&A line.
I'm looking forward to it. Let's get this cracking. Over to you, Cray.
Excellent. My part's going to be very simple and very straightforward on this one. I'm just doing an intro for the experts who are on board here and making a little bit of a plug backwards to our previous webinar that we had where we talked about structural modeling of hydraulics for 1D, 2D, and 3D. In that capacity, in that webinar, you can look it up on IceWarm's website or on the YouTube site. Have a look at that one. We got mainly into the limitations of 1D and 2D, talked about how it's handled there, and just gave 3D a cursory mention. Now, we decided at the time due to the responses that it might be worth holding a whole webinar just based on 3D. So that's what we're doing in this case. That webinar focused mainly on the fact that 1D and 2D models are depth averaged, and that we've got these, anything in the vertical profile is going to come out as the same velocity, and anything in this cross-sectional profile is going to come across as this average velocity here. That's something that we've discussed in that webinar in particular. And now, hang on, I'm going to annotate my screen here so you can see this with the spotlight. Again, anything in a 1D or 2D model is going to ignore this whole vertical profile variation, the boundary layer down here being 0, coming up to your maximum here, and it's going to just average it as a single velocity in the water column. Likewise, if I go straight up and down here, that's going to be the case in your 1D and 2D models. 3D doesn't necessarily have that limitation. Now, I do want to talk about the AR&R, because this is an Australian water school that's hosting this. We'll talk about the Australian rainfall runoff guidelines, and other jurisdictions may have their own. And looking at the worldwide audience, not everybody's going to be interested in what's going on in Australia, but it's kind of a representative of how the industry has been handling 3D modeling in the past. In 2012, Australian Rainfall and Runoff came out with this report that barely gave 3D a mention. And what we had here basically was the limitations of 3D modeling. And it said in 2012, computational speeds may reach a point where 3D computational fluid dynamics approaches become a viable tool for hydraulic modeling. Now, we've had, 8 years since then. I think we're at that point. It is a viable tool, and it probably always was. Even at that point, it was a viable tool for certain types of hydraulic modeling. What they did tell us, though, was it's not practical to apply at the floodplain scale. We'll find out about a few of these applications today where we can go into a Farfield environment and model some things in 3D that are a bit bigger. Now, obviously, this text is too small. I'm just getting an excerpt of this, but in the 2019 guidelines for AR&R, 3D got more of a mention here, and I'll just pull one excerpt out of here, and that is, again, the limitations of the 3D model that are mentioned here. If you're going to model a river, it ought to be a short reach, they say, or if you're going to model a structure, we can go right within that individual hydraulic structure. And the warning that they mentioned here is still relevant. It is very heavy computationally. We'll talk about that today in a few minutes. Wanted to just show 3 examples, one of a 1D, a 2D, and a 3D. This is a 1D model. Even though we look at it in 3D, it still is being built out of cross sections where flow is perpendicular, absolutely perpendicular to the cross sections, can only go in one dimension and one direction. We move that into 2D, and we can then see more than just the one dimension. We get 2 dimensions, and also more than 2 directions. We get an infinite number of directions, but all in a plane. So any one of the 360 degrees, we can see the flow moving in a 2D environment. Again, this is depth averaged. Every grid that we've got here contributing to the this animation is allowed to transfer flow laterally in any direction, but it is depth averaged. We go into 3D. And in 3D, we're able to take culverts that only have one inlet and one outlet and one slope in a 1D and 2D model, and see what's going on inside. And so you can see the backwater coming up, and you can see energy dissipation, and the coefficients that you would have to otherwise enter in a 1D or 2D model can be actually computed in your 3D software. Now, where's the limit going from here? I'm going to say 4D. What happens if your culvert looks like this? This is now a moving culvert. If time is your 4th dimension and you can move your structure through time, I guess you could call that a 4D structure. You never know where things are going to go from here. And so this is what is exciting about this subject to me. You can do things that were previously absolutely impossible given hardware and software advances. We can do things now that you couldn't have done before. So I'm excited to hear from Mitch and Ben. We'll turn the time over to Mitch to talk about some Farfield modeling, which is going to be a large-scale 3D models setup, and then Ben will talk about zooming in on individual hydraulic structures. So with that, I'm going to stop my share and turn it right over to Mitch.
Thanks, Craig, for the introduction. I'll just share my screen out here for you. All right. Well, I'm going to be talking today primarily about the 3D shallow water equation solvers, but I'll also start by comparing CFD, which Ben will talk about in a lot more detail with them. I'll be talking about the scales of near-field modeling versus far-field. And once we go into the far-field modeling, talking about 2D versus 3D applications for those types of models. And then we'll wrap things up talking about the data and validation and visualization of 3D models and the extra things that you might need to consider. So computational fluid dynamics, and I'll refer to them as near-field from now on, but they're really the CFD models. They've solved the full Navier-Stokes equations, and they aim to resolve or represent very fine-scale turbulence. And by turbulence, I mean eddies, essentially. They can only go down to a point because you can't keep going till infinitum, but they are really trying to resolve as much as they can. And they look at the conservation of mass and momentum as energy as the core equations that they're solving. And because of the detail that you need to go down to with these models, they can be computationally expensive. And so, computers are getting faster and faster all the time. And, over time, we'll see these models become more and more prevalent, as Cray alluded to. In the top right-hand side over here, this is a vertical slice through a CFD model, OpenFoam. And there's a diffuser port down the bottom here. And basically, we're seeing the jet flying up off the, well, not flying, but flowing up off the bed. And in this area, there's very fine resolution to try and capture how that jet is dispersing into the water column. And you can see that the grid is unstructured both in the X direction here and also in the Z direction. The 3D shallow water equation solvers, and I'll refer to those as Farfield models from now on, are derived from the Navier-Stokes equations. And the main difference is they assume this thing called the hydrostatic assumption. So that means that the pressure gradient force in the vertical is balanced by the acceleration due to gravity. But basically what we're saying is that these models assume that there's negligible vertical accelerations. You can still have flow in the vertical, but you can't have accelerations. And so also, rather than trying to look at individual eddies and turbulence, what these models do is they look at fine-scale horizontal and vertical mixing of turbulence represented by eddy viscosity and scalar diffusivity terms and models. What this means is that these models can be run over much larger spatial scales and time scales, and I'll talk a little bit more about that in a second. So this is an example of a near-field model, CFD, OpenFoam. So this is an outlet here. It's about 0.1 of a meter across, and it's discharging into 20 meters of water depth. And so spatially, we're talking about orders of millimeters to meters. Across this diffuser jet nozzle, we've got elements that are as small as 8 millimeters going up to sub-meter. So this mesh down in the bottom corner is an adaptive mesh looking at how the flow is behaving. There's almost 17 million cells that are representing that area. And the model's only a couple of 100 meters across. Temporally, we're looking at sub-second to hours. And this little blue information here is basically results from the CFD model. Now, if we want to understand how that diffuser and how the contaminants, once they've been initially mixed, move out into the wider environment, whether it be the ocean or a river or even a floodplain area, we need to look at larger fields. So the effects of tides and ocean currents, winds and waves and densities, lake filling and closing. Spatially, these things happen over meters, so that might be both in the horizontal direction, but in the vertical direction. And in the horizontal direction, we're talking about kilometers. And these processes might happen over seconds, but some might happen over months. Long-scale ocean eddies or flood behaviour in a river. So what we're doing here is we've got this is actually a 2FE model. It's a couple of 100 kilometers long. We're zooming into the area where the diffuser is. And what we're doing with this model is we're using kind of the best of both worlds and combining the near field model, which we're taking the results from, and applying turbulence and mass into the far field model as a boundary condition. And so on the right here, we're showing these concentration fields both in plan and section view as they move away from the diffuser over very long periods of time, weeks. Okay, so it's good to have a really wide range of people on the line here. I'm trying to sort of answer some of the reasons why you might use one solver over another. And so if we're looking at choosing a solver, what's important to our problem? You know, are we really needing to look at those fine scale eddies? Are they critical? Is there significant vertical acceleration like a diffuser? Is there mixed phase behavior? So, you know, air and water both being needed to be modeled, or is there some sort of, you know, hydraulic structure that's basically applying some sort of force in the water column that we need to represent? If any of that stuff is yes, then, you know, CFD or a Nearfield model might be more appropriate in the area that you're looking at, or a combination of CFD and a Farfield model, so the best of both worlds. If no, then we can open up some pretty interesting opportunities in that we can look at really large spatial scales and temporal scales in either 2D or 3D, and we can look at complex hydrodynamics, sediment transport, and water quality over these scales. What I'll talk about next is in what situations should we have a look at 3D versus a 2D model in the Farfield. So as Craig, you know, was alluding to earlier, you know, 2D models are depth averaged, but they are really useful for a lot of engineering applications, and particularly floodplains where friction tends to dominate. But what about systems that don't really behave in this way? They don't have flows that go in one direction. They might have counter currents that occur at depth. And what about things like stratification or density-driven flows, secondary currents in meandering rivers, or where the vertical variation in the concentration profile, like sediment transport, or light, so light penetration of the water column, is important to capture. This is just one of many examples I could have shown you, but it really highlights the difference between some of the things you can capture in a 2D versus a 3D model. And so what we're looking at here is what we call a salt wedge estuary. We have typically fresh water flowing down a river. We have salt water coming in from the ocean. And we have a halocline that forms in between these two layers. And essentially, you've got the fresh water floats over the top of the salt water, and there's very little mixing between the two. And that can really affect the fate of contaminants that you might put into that system. So this is a Yarra River model in southern Australia. The yellow mesh here is the horizontal mesh that we're applying, the flexible mesh. We apply our flow conditions, so fresh water to the upstream boundaries. We've got our astronomical tide downstream, which has got salt. These have got temperature and salinity assigned to them as well. And because we're looking at baroclinicity, at effects of density, we have to have temperature on. And because we have temperature on, we need to look at things like solar radiation, evaporative fluxes, wind speeds. They all need to be added to the model. So we're building up this complexity already. And then in the vertical, we essentially are slicing up the model. You can think about it, I guess, like a lasagna, in that with these shallow water equation models, instead of having an unstructured mesh in the vertical, we can essentially chop them up into bits. So this is a 0.2 meter resolution grid. These are the results from this model over about 16 kilometers, so quite a long distance. We've got the tide coming in down at the port here. We've got fresh water coming in from upstream. The red is salt water, so about 35 ppt. So the salinity we're showing, fresh water coming in from upstream. And so what this is showing is that the fresh water moves across the top of the salt water, and there's limited mixing of those two systems. They're essentially acting as two water bodies. So why does this matter? Well, depending on the application we're looking at, the pollutant fate might be really affected by this. So the top picture here, all of these models we're putting in the same concentration of pollutant. The top model is a 2D model, and the bottom one of the other 3D model is the 3D model that I just showed you. So in the middle picture there, we're applying the contaminant into the surface freshwater layer. In the bottom picture, we're applying the contaminant at the same location, but into the bed or close to the bed. And the top model is the 2D. So the 2D model, right, it's got one velocity, one concentration per cell, it's depth averaged, and that's the result you get when you're looking at advection dispersion with a 2D model. If we put that same contaminant to the surface, it kind of cruises along the top and goes out into the bay, and maybe that's not such a problem unless you're a flying fish or something, and you wouldn't be too happy about that. The real problem comes is if you put that same contaminant into the bottom layer, it just sits in that salty saline water and just continues to concentrate. And so having that 3D knowledge of that system has a massive impact on how we might dispose of a contaminant. So it's as easy as just turning on a switch, right? You know, we get a horizontal discretization of our model. We go and we look at the vertical. Yeah, sure. If you like to live dangerously or like garbage, then go for it. However, real 3D modeling requires you to represent key processes that influence the vertical structure of the water column. And so you're really looking at this additional dimension to conceptualize, to calibrate, and to validate to. You need additional data, so it's not just water levels and velocities at a point. You need to understand what's happening through the vertical water column. And also, baroclinicity, so temperature, salinity, velocity measurements at the top of the water column and below, things like ADCPs and atmospheric data. And in the case of stratified systems, vertical mixing can be sensitive to the way that you discretize it, how you're layering the model. And so you need to do sensitivity testing and validation to data of those processes. And visualization. We need to be able to have clever ways of slicing through the vertical to validate and to see these results. And it's really critical. So Ben will have some pretty cool visualizations of these types of things. So, and Ben will also go into a lot more detail in some of those finer scale issues. So I've briefly covered today is what's the scale we're trying to capture here? Are we looking at very fine scale velocity and profiles, or are we looking at a larger scale? Nearfield versus Farfield, picking the right tools for the job. 2D versus 3D Farfield modeling. Is a 2D model appropriate for what you're looking at? Can 3D do a better job? And it's not just as simple as turning on a switch. We've got density and water column data, extra dimension to calibrate to, and data describing the vertical structure of the water column. So thanks very much for that. I'll throw it over to Ben, and happy to answer any questions later on.
Thanks, Mitchell. All right, so we're moving to smaller scales here, a little more sophisticated modeling, computational fluid dynamics. So 3D CFD is what I'll be talking about, in particular how it fits in kind of in the range of spatial and time scales that Mitchell was hinting at, and then showing some hydraulic applications of CFD that I've come across in my time at Alden. Big picture, the scales of environmental flows. So you think about water, the way water moves on our planet, we could, different processes have different time scales, they have different length scales, and that's kind of the theme of this webinar. So we have stuff that happens on the order of days to years with very long spatial scales of, say, hundreds of kilometers. We're thinking about ocean circulation, eddies in the ocean that are influenced by the planet's rotation, tides, baroclinic fronts in the ocean. If we move to smaller scales on the order of hours to days, we're starting to get into the realm of engineering applications. So we're talking about hours to days, tens of meters to kilometer scales. So river flooding, estuarine circulation. If we move down to smaller scale processes, now we're really getting into engineering interests, surface waves, hydraulic structures, discharge plumes. So we're talking, on the order of seconds to hours and, centimeters to kilometer scales. On down into the scale of the turbulent eddies, right? Motions that are of importance to fish and to small scale mixing and to the dissipation of turbulent energy into heat and mixing at molecular scale. So you have this kind of cascade, you can think of it from large to small scale motions, and as energy moves from larger to smaller scale motions and ultimately down to various fine scales. So this, spectrum of scales presents, there's sound waves in there for reference, and then for folks interested in sediment transport, that's a particularly challenging problem, right? Because you've got stuff that happens down at the grain scales, the scale of individual sand grains, all the way up to very long time scales and spatial scales of fluvial geomorphology and landscape evolution and channel migration. So as I was saying, this presents a problem to the modeler, right? We need to look at what we're interested in and what's the best tool. So there's a hierarchy of models that have been developed. So we start at the very small scale, direct numerical simulations, DNS. These are CFD simulations where we're explicitly resolving those turbulent eddies that Mitchell was talking about, all the way down to the very smallest eddies that ultimately get smeared out by viscosity. Now, those are really limited to very small millimeters, second, sub-second type simulations, and mainly in the academic world. Moving up to large eddy simulation, here's a simulation of flow, unstably stratified flow over a block in a channel. And you can see the rich structure of the turbulent eddies. With large eddy simulations, like it says, we're resolving the larger eddies, but our grid only goes down to a certain point, and there's still eddies going on below that spatial scale that we have to parameterize their effects on the flow using some kind of subgrid scale eddy viscosity type model. Moving up to larger scales, RANS, Reynolds Average Navier-Stokes CFD. This is really the workhorse for the hydraulic engineer at this point. We're talking scales of applicability from seconds to hours and from centimeters, up to tens of meters. Moving up into Mitchell's realm of these so-called hydrodynamic models, right, based on the shallow water equations. These can be 2D or they can be 3D. It's important to note, though, that how most of these hydrodynamic models that are 3D are 3D in the sense that they're allowing for vertical flow, but they don't necessarily solve for a vertical momentum equation. So they're not great for rapidly varied flow, for flows with heavily distorted free surfaces, and those kind of applications. Finally, up to climate models at the very large, say, kilometer grid scales, where there's lots of subgrid stuff going on that needs to be parameterized. So CFD RANS, that's mainly what I use at Alden. We do a lot with hydraulic structures. Here's a spillway, a step spillway. And you can see the grid superimposed on these plots of velocity. And now this is the actual velocity from the RANS solution. So I should have said that RANS, the Reynolds Average Navier-Stokes. So we're averaging the Navier-Stokes equations and essentially smearing out the turbulence. So we get a nice smooth flow field, but we have to parameterize the turbulence using an eddy viscosity model. So we're not really resolving the rich structure of the turbulent eddies, but we're including their effect in the turbulence model through, say, K epsilon model or K omega or something like that. But really, they're really useful for rapidly varied flows where vertical acceleration is important. And here's a hydraulic jump at the base of the spillway where you have a lot of vertical structure that's important to pick up that a 2D model would not pick up. So the pros, fully 3D solutions based on Navier-Stokes equations. They're cheaper than physical modeling, and they're good for comparing alternatives of, say, different modifications to a hydraulic structure, especially in a qualitative sense. The cons, spatial and time scales, as I mentioned. Uncertainty. These are approximations for the actual governing equations, right? So the numerical methods you're using are important. Your grid resolution. How accurate are your subgrid scale physics, say your turbulence model? How good are your inputs? How well do your boundary conditions, for example, agree with maybe what is actually going to happen in the real world? And they require users highly skilled in both fluid dynamics and the numerics. Another application. So this one was looking at fish protection at an intake screen. So these are about 10 meter long, so-called T-screens, where we have perforated sections. And here's a picture of one. So these are, centimeter scale pores in this thing. And the client was interested in looking at the boundary layer over these intake screens and looking at the potential for fish entrainment and fish entrapment. And so I did a simulation. So we're thinking about a wide range of spatial scales, right? We got the spatial scales of the fish and the pores at very small scales, all the way up to the, it's coupled to the larger scale flow patterns around these structures. So this was actually a Fluent model using an unstructured grid. And I actually did resolve the holes along one strip of this intake screen. And then my compromise, you can't obviously have it resolve every single one of the holes. So it was to parameterize the rest of the intake screen using a porous jump. Essentially this artificial way in CFD to simulate drag across some kind of, say, porous baffle. So there's a zoomed in look at the mesh. You can see the unstructured mesh allows you to really focus in on the scales of interest, but not drop the larger scales as well. So we're able to pick up those larger scale motions like the bow waves on these things, the wake regions, while also being able to look at the very fine scales of, say, the recirculating eddies in these holes and stuff that's, you know, of the scale of the fish. I wanted to touch on sediment transport a little bit here. Because that's kind of a new cutting edge thing with CFD, and talking about its applicability in hydraulic applications. As I mentioned early on, sediment transport is particularly difficult because there's a lot of uncertainty in it. You know, there's so many variables that go into sediment transport. You know, predicting entrainment, predicting transport rates of both bed load and suspended load. Over long time scales and with a lot of temporal variation. It's extremely difficult problem. So, you know, you could think of it at, like I said, on the order of, you know, landscape evolution or, you know, meander bin evolution, the formation of point bars, obviously prohibitively large space and time scales for CFD. Now, there are some morphodynamic shallow water models that will allow you to kind of approximate how things change on, say, weekly type scales. Again, a lot of approximation there. With CFD, Flow3D, I would say, is probably leading the way on developing a sediment model that couples with the hydrodynamic model. The Flow3D scour model, which Brian knows a lot about, Brian Fox, who's one of our panelists. And I'll be talking about that here in a second. What's important to remember is that there's a lot of subgrid scale stuff that goes on at the grain scale, a lot of uncertainty about entrainment that has to be parameterized. So let's look at CFD, a CFD application of sediment transport. So here is some images from Flow Science provided by Brian Fox. Their model in Flow3D basically accounts for several different processes associated with sediment transport, right? We have sediment particles that are in suspension being advected by the mean flow. Those particles have a tendency to settle. So there's assumptions about settling. They pack the bed. The bed is actually allowed to grow or aggrade or degrade. They can be re-entrained. There is a model for mixing and suspension of those particles by turbulent eddies. Remember, we're not actually explicitly resolving turbulent eddies, but there is a model to approximate that process, as well as bed load transport. And the entrainment and bed load transport are primarily based on empirical equations, based on lab and field work. So as I said, there's many small-scale processes going on that must be parameterized, these sub-grid scale processes. So I would definitely caution the user that while this is very exciting and cutting edge, that extensive calibration and tuning of your model is definitely advised. However, Brian has written a paper and done some work showing some preliminary validation for this type of application where you have flow around a bridge pier and you get these three-dimensional horseshoe vortices that set up and create scour. I'd say this is a really good application of this model where you're talking about kind of equilibrium conditions, stuff that happens over relatively short time scales at smaller spatial scales of, say, like a bridge pier. Here's some work that I've done with Flow3D's sediment model. So working at Alden, I have the benefit of also having access to some physical model results. This top picture here shows a a laboratory flume. It's about 36 centimeters deep, and there is a section of live bed. So there's sediment, sand-sized sediment, this white stuff here on the channel bed. And then there's these 3 isokinetic suspended sediment samplers down here at the downstream end. And we ran flow over this and watched the sediment suspend and then measured the concentration downstream. And so then I set up a Flow 3D simulation of this exact setup and did some calibration work. So I didn't just take it out of the box. I did some tuning to try to match what I was seeing in the lab with the CFD. And so here's the 3 probe points that correspond with the 3 isokinetic samplers. And this plot here shows the red dashed line is the lab observation of suspended sediment, and the kind of squiggly line is the CFD. As you see near the bed, the CFD is nailing the suspended sediment concentration. As you get further up in the water column, this blue line, it's predicting about 1 milligram per liter, whereas the lab was more about 10. And then high up in the water column, the CFD is basically predicting nothing, yet the lab is still showing 5 milligrams per liter or so. So at this point, this brings up a really important point. You're seeing some bed evolution, some scour here. We actually didn't see that in the model. We saw dune formation with formation of bed forms. And I think it's important to remember, again, that there's small-scale processes related to turbulence that aren't fully captured here. And so what's going on is you have these bursts that come off the bed. They actually advect sediment up, these eddies advecting sediment up into the water column, leading to more sediment higher in the water column in the lab than in the CFD. So there's just a lot to think about with this sediment model, I guess is my point. And there's a lot of subgrid stuff going on that you need to be thinking about. And I would really caution anybody from taking it right out of the box and using it. That said, it's very exciting. And I think there's a real opportunity for tuning this to your particular application. The takeaways here, quickly, many scales, many models. It's important to think carefully about which one's best for your application. And sometimes there might be 2. Sometimes you might need a shallow water model that feeds your boundary conditions to your CFD model. And as commercial codes become increasingly user-friendly and incorporate more physics, more subgrid scale models, it's important to acknowledge that there's still uncertainty with these. So important questions I would suggest asking of yourself is my model converged? Have I run it long enough? What are the accuracy of the numerical methods I'm using? How dependent is my solution on the grid size? Have I resolved my model enough? What are the influence of my boundaries? How close are my boundaries too close to my area of interest that I'm getting some artificial influence there? What are the assumptions that my subgrid scale models are built on, especially around shear and drag? And I really, really encourage people that if you're going to get into CFD, do some simple validations, whatever code you're using, against simple textbook cases that we know the answer for. Say drag on a sphere, predict the drag coefficient. Is the CFD getting it right? Head loss in a pipe. What's the energy grade line on my open channel? So I would do some kind of sanity checks before you just start diving into using CFD models. But if used properly, I use it every day. CFD is an effective tool for the hydraulic engineer, especially good if paired with lab or field calibration and validation data. But it's no replacement for your brain. Don't be tricked by pretty colorful plots. And as always, trust your engineering judgment. So with that, I think I'll kick it back to Trevor.
Fantastic. Ben, Mitchell, Craig, what a load of, that's what we do. The trouble is the webinars put together an enormous amount of material in a very short time. Over to you, Craig.
Sure. Hey, thanks for that. Really enjoyed those presentations.
Yes.
Do keep those questions coming in. Thanks, Owen, for that one. I think we will cover that in a little more detail. But I'll add a little bit to that, and then hopefully we can also get Brian to come on board and answer a few questions about some specific hydraulic structures. The question that came up then about the Yarra River model, I guess I wanted to expand on that a little bit. So Mitchell, I know some people on board might be wondering and looking for rules of thumb, which are probably tough to give, as far as setting up a 1D or 2D versus a 3D model, and both in terms of the development time and in the computational runtime. So I guess because you've mentioned a specific model, the Yarra River model, I'll ask the question, on the development time, that same model, setting it up for a 2D versus a 3D application, what were the time differences there? And then on the computational runtime, how long did the 2D model take to run versus a 3D? And did you even run them on the same systems, or did you need a souped up system to run your 3D? And that leads then straight into, if you can maybe answer live a little more on the detail that Owen asked about, and provide us with some details on that. So over to you, Mitchell.
Yeah, so the first part, so the horizontal mesh, you're setting that up, and you're trying to get that as efficient as possible and having resolution where you need to. The actual mechanism to allow for 3D isn't too tricky, but what you need to have though is you need to have the data. I showed a slide there with some salinity and temperature measurements, and an ADCP transects where you're looking at velocity profiles, so that in any type of modeling, you're needing to have resolution where you have high gradients of anything, whether that be momentum, mass of salt, or temperature. So the time's really, I guess, not so much actually flicking on the 3D settings, but optimizing that and doing sensitivity tests to that. In terms of the runtime, it really depends on how many vertical layers you're going to, but a rough rule of thumb is if you have 20 vertical layers, the model might run, say, 5 times longer than it did previously. And I think, if you start to turn things on like morphological analysis or, sediment transport, then that can beef things up as well. So did that cover all the questions? All right, on this one?
Yeah, I think so. That one more question has come up, and then we'll probably turn it over to, I think there's a question for Ben on there as well. But the one question corresponding to FV, does TwoFlow use a RANS solver, and can you choose between different solvers like K epsilon, omega, SST, etc. in TwoFlow FV?
Yeah, so there's for the horizontal advection, there's like the Smagorinsky equation, and you can either have that or a constant eddy viscosity model, essentially, for vertical turbulence. And this is just to back what Ben said earlier, these shallow water equations models are usually assuming that things in the horizontal are a lot, higher gradient, or so not gradient, but the processes in the horizontal are more important than the vertical. However, we tend to use the Gotham ocean model, and that does transfer momentum and mixing between the different layers. So we don't have a RANS solver, but we are using bulk velocity and buoyancy values from the model to drive that momentum mixing between the layers.
Great. Cool. You may want to read this question, Ben, yourself, about the Flume test. So I'll turn that over to you to answer that, and then maybe we could have Brian Fox answer the question. It's a general one. Do you have some fundamental recommendations for developing free surface 3D modeling? So that's just fundamental recommendations. It'd be great to hear from Brian since you're on board. But in the meantime, Ben, if you can just have a look at that question on the Flume test from James, see if we can get some answers for that on that verse about the grid.
Yeah, James, that's a great question. James is asking if I looked at large eddy simulation in a finer grid instead of the RANS approach for the suspended sediment and entrainment. That's a great question. I did run an LES simulation. I have not processed the results yet. But I will say that there's still some question in my mind of whether you're going to get the actual small scale physics required to build the dunes in the first place. Now, it would be interesting to do a laser scan of the bed, put that fixed into your model, and to see if it, or put it into your model as a packed bed that was erodible, and to see, then turn on the LES and to see if you got those bursts and to see some dune migration or something like that. But it's just something I haven't really looked at, but definitely thought about.
Excellent. Brian, I don't know if you're able to come online with your camera.
Are you able to hear me? Okay.
We can hear you okay, and we can see a photo of you.
Good. So yeah, I'm happy to help answer some of these questions. So the one from Jorge is do we have any fundamental recommendations for developing free surface 3D modeling? And so in short, yes. So with Flow 3D, the software is really designed for free surface applications. So the developer of our software actually developed this method called volume of fluid, which is a special numerical method for tracking the interface between the water and air. So almost all of our setup in Flow 3D is geared towards those types of applications. So beyond that, really kind of fundamental aspects of a model setup are going to be developing a good geometry that represents the structures that you're trying to model, getting a good mesh that's going to help resolve all of the important hydraulic characteristics, including the important physics, which for basic free surface is going to be gravity and turbulence. And then, running and doing, really good validation and testing as Ben had suggested in his presentation.
Great. Thanks for that question. There was also a few others now that I'm going to have, I think, Mitchell answer these live. That's the indication, at least on the Q&A board. Talking about non-Newtonian fluids. Now, this will be a plug for those who are HEC-RAS users on the call. The developers of HEC-RAS have just come up for the second annual Pub and Grub in Portland and discussed what's coming new in HEC-RAS. One of these is being able to model non-Newtonian fluids, like for a tailings dam break and things like that. Go to the HEC-RAS blog, just Google that, and you can see the presentations on what's coming and get a discussion for, you can actually see the presentation about all the different fluids and, mud flows and debris flows and the hyperconcentrated flows and how we might model those sorts of materials. There are models that can do that already. That's going to get added into the free HEC-RAS software as well in the next iteration. So have a look at that, and then I'll turn that question over to Mitchell. Can we do that in some of these models that we've discussed today?
Yeah, so I guess from the shallow water equation type models and in 2D and 3D, we can do these things. So 2Flow can do that in 2D as well. I'm working on the 3D stuff. But again, it's sort of a matter of scale. If we're looking at, say, a dam break where we've got a large floodplain, looking at how far that moves downstream, then we should probably look at that in a shallow water equation model. But if we're looking at, say, some dredge material and how that settles out over time with very complex processes, or maybe there's multi-phases involved, then something like a CFD model can do that very well over a smaller scale.
Great. And I think there was one more question that you said you wanted to answer live. Let's go ahead and move right to that one.
Can I just add something to the
go ahead.
question about non-Newtonian? This is one that comes up all the time. This has been a really hot topic where people are interested in modeling tailings dams with non-Newtonian models. There's some within Flow 3D, we have some really interesting capabilities for non-Newtonian and 3D modeling framework. But as Mitchell stated, a lot of these problems have very different scales and it requires some 2D integration. So I think there's some really interesting opportunity for 3D, 2D integration for tailings dam breaches. Modeling the breach area with the 3D models, and then integrating that with the shallow water for some of these larger scales.
Excellent. And so, I think the question, no, Ben, you answered that one for them, but then also suction pressures at structures is another question that's just come up.
The answer is yes. We have used ran simulations to look at, for example, drawdown forces on gates, where you have flow accelerating underneath the gate. So you get an acceleration of velocity. Higher velocities lead to lower pressures, and therefore you get a down pull on the gate. So the answer is yes. I would say if you have anything to kind of sanity check or test against or validate your model first, I would encourage you to do that too. So when we start talking about drag, for example, that's really highly dependent on the wall function you're using and the turbulence model. So be careful there.
Thanks. Another question that's up there is as far as presentation of materials to a community group or to stakeholders potentially. People who might not understand the difficulties of moving from 1D to 2D and then from 2D to 3D. And I guess this is just one that I'll just mention a couple of comments about. In Australia in particular, where we've got large open pit mines going in right next to some river systems, sometimes those are requiring massive spillway structures and things like that our 1D and 2D models aren't going to be able to model very well, in addition to some spillway upgrades. Not a lot of large dams being built in some of these countries like Australia and in the US, but sometimes these spillways are being upgraded. And the question did come up on spillway models and what is the best way to simulate one of those. Well, if you watch our 1D, 2D structures webinar, you'll see that some of the assumptions in a 1D and 2D model start to fall apart when you get any slopes above about 10%. Well, a spillway might be anywhere from 10, 20, 30, 40, up to 100% slope or more, and then you get all the air entrainment and the vertical mixing where you would need to move into a 3D model. The limitation then being that you could model a few snapshots of time, a few minutes worth of the max condition, but it's going to be very difficult to model a whole flood coming and going over weeks of time. So that's just a general comment based on the questions that have come up on the best application for a spillway model. Anybody else want to comment on which software you would use to model a spillway?
Yeah, it's definitely within the realm of CFD for sure. And Flow 3D, I would say, has a little bit of an edge because of the VOF solver, the volume of fluid free surface solver that Brian mentioned. So we only have to solve for the fluid itself. Some other models require solving the equations for both the fluid and the air, and may or may not give a very sharp interface between the two. But definitely within the realm of CFD.
Great. I think, Trevor, we may want to just go to closing comments. I'll leave it to you for some housekeeping items.
No, it's fantastic. Look, if I was given out prizes for today, it'd be going to the scouring model, Ben, the isokinetic scouring model. Every time you guys put something up, it's moving, and that really helps people understand stuff. So you've really gone out of your way, each one of you, to make this a really interesting. And as I said before, it's doing a lot of stuff very quickly, and to have models that move, that's really helped a lot. But the graphics are fantastic. But that I don't even know what isokinetic means. Don't go there. But thank you for all the effort in communication. It's fantastic. Particularly Craig for taking on the technical sharing of today, and Brian for joining us to contribute to the discussion. It's been fantastic. Ben and Mitchell, we have really enjoyed this. I've appreciated everybody's input to today. I think that's where I'll leave it for now. There's no more questions coming on board, but I've really appreciated your time in joining us, everyone who attended, and for the presenters and panelists. Thanks so much. We look forward to getting together again. Is there something I'm leaving out? Really, there is one other thing. Thank you, Joel, for your background work in this. And it's not seen, but there's a green Australian Water School logo. That's Joel right there. Appreciate your effort in that. Thanks so much. We'll leave it at that. Thanks for joining us, everybody. And thanks so much, panelists. It's been great. See you next time. Bye for now.
Subscribe to this YouTube channel by clicking the subscription button. For future webinars and online short courses, please visit our website at australianwaterschool.com.au.